Okay, in this video here we're going to show you how to do a temperature sweep here. So I just created a new mixed analog blank schematic and I called it temperature diode here. So I'm going to do this with an example here. So first off, we're going to build a very basic circuit. So we're going to place parts. Now the library, I've got lots of libraries installed here because I do lots of different things. The library you need installed for this and for your homework is the diode library. Now the diode that we're going to use is a 1N4001, but if you try to do 1N4001, it's going to say that there's nothing there. A lot of these that you will need here, they actually start with a D, and it's going to be D1N4001. That's a standard diode, and so I'm going to place that part, and I'm going to place it rotated in that direction. You on your homework will be doing a 1N4148, so it would be a D1N4148. And then let's see here, what do we need? We also need a voltage source. So let's go voltage source, VDC. Now I'm going to be doing the voltage and current curves for this diode. So I actually don't need to put any voltage on this because I'm going to sweep this voltage. So then we also of course need a ground. So G for my ground. Put a ground in, and then of course we just wire the circuit up here. And so it's a very basic circuit. Now we need to set up simulation profile. So I'm going to say temp DC sweep. I already got that profile name, I've already done it, so I'll just call this DC sweep 2. Just so we can show all the settings here. So we're not going to do a transient, we're going to do a DC sweep because I want to do a current voltage curve. So the voltage source of course was V1, and then the start value, we're actually not going to do 0, I'm going to do 0.01, and I'll show you why in a second that I'm not doing 0 here. And believe it or not, I'm only going to go up to, well, let's go up to 1 volt to start with. We might change that. 0.01 increment. You have to be careful on your increment. If you make it too fine, it's too many data points. But that's not the only thing we want to do here. We want to see what happens with temperature. So I have a primary sweep, and then you can see here there's this temperature sweep. So I can do a temperature. You can run it at a specific temperature if we only want to run it at one temperature, but we want to run it at several temperatures. So let's do this at, for instance, -40, 0, 27, and let's say 70, well, let's do 125 like suggested there, so running it hot. Alright, so now it's going to run the simulation 4 times at those 4 temperature settings. So we've got that set up. The other thing we need to do is put a probe on. Now I'm not going to measure voltage, I'm actually going to measure my current. Now you have to be careful. Some people try to put their current on a wire and it's not going to do that. So it'll ignore it. You actually have to put it on a component. So you can see here where I'm right up against the diode and I can put my current probe there. Then of course we just run the simulation like we normally would. And we wait for it to pop up here. Now once it's done simulating, notice that it gives you all 4 of these traces. If I leave them all highlighted, it's going to plot all 4 of them at the same time. So let's go ahead and just say OK. And we can see, hey, it's plotted these 4 curves. Now you might say, yeah, but I don't know which one is which. Well, you can always right click on it and say trace information. So that yellow curve is 125 degrees. So actually what we can notice here is that at lower voltages we have more current at higher temperatures, which is maybe a little bit different than the example we did in the class the other day. However, remember these are actual diode models that are much more extensive than the ideal current and voltage relationship, and I can show you what we mean by that in a second. Now this is all well and good. We can see, okay, well, it's definitely got more current. We can kind of examine what the effect of the temperature is, higher current. We should also notice that the turn-on voltage is much lower for the higher temperatures. You could also do some different ranges here. But one thing I want to point out here is that because this is an exponential function, one way these are often graphed, especially if you're looking at data sheets, is they do a log value of the y. And the reason they do a log value of the y is that then if you have an exponential function and you take a logarithm of an exponential function, you get a straight line. And you can see these are relatively straight. They're not perfectly straight, but I shouldn't think they would be, because again, these are just ideal diode equations, would be just a pure exponent, but these are real models. So these aren't just the ideal equations, these are real models for it. And so we can see it, and in this way we can kind of see, especially at lower voltages, there is quite a big impact on the temperature. And what do I mean here? Well, at 0.2 volts, we've got just below 10 nanoamps. But then and this is at the -40, this would be at the 125, and you've got 100 microamps. So 100 microamps and 10 nanoamps, that's a huge difference as far as magnitude of current. 100 microamps you might still think is a small current. It is. But if you're thinking about this not being turned on yet, that's a huge amount of, quote, leakage current, which would create even more heat. So it could cause an issue. So you have to see how these things vary with temperature. All right, so let's go back to the simulation here and just show you a couple things as well. Oh, as a side note, I'll go back here. You can also re-click, take that log off. In some cases, come on. There we go. In some cases, you would want to do log x, but you can. In this case, you really wouldn't want to. You want to leave it as linear, but you can do that as well. But let's go back and take a look at this a second here. And the last thing I want to show you here is if you right-click on this diode, you can see Edit Part, but you can see Edit Properties and Edit PSpice Model. So I'm going to open up the PSpice model here. We're not going to actually edit it, but if you work for a company, and actually Professor Byers tells me this, is that the way they develop their PSpice models is they get the components in, do all those measurements on an actual piece of measurement equipment, and then go ahead and create their own models. So what we can see here is, well, first off, remember that parameter n we say that we take as 1 unless otherwise specified. Well, we've got this here being 1.984. Band gap energy, because it's silicon, is 1.11. It's got a lot of other parameters in here, which I don't know all of them. Junction voltage, reverse saturation current, 14.11 nanoamps. Notice that junction capacitance, that zero junction capacitance we have here. Now, we could go ahead and change these properties here and see what happens with that. I don't want to do that because I want to not edit the library within PSpice. If we were to do something like this, we would create a new part, and maybe we'll do that in a later video, show you how you can create your own models. But I did want to show you that it's not just that ideal diode equation. Look at all these other parameters that are in here. Alright, so no, not going to save changes. So very quick, easy thing. Now what I expect is I want to see both this graph, I also want to see it in log, and I want you to talk about some of the features, the effect of temperature, how this affects current, and talk about how many times greater, for instance, 10 nanoamps versus 100 microamps. How many times greater is that? That's significant. Things of that nature, and any other things you might see when looking at these graphs. Okay, so that will be your assignment that's due in class.